Today, we're going to decode the chemical blueprint of one of the most essential materials on the planet, concrete. And we're going to see how a surprisingly simple-looking map can actually predict its future. I mean, think about it. We see the finished product all around us. Buildings, bridges, you name it. But the real magic, and honestly, the real headache, happens in those chaotic first few hours right after you mix cement with water. Everything, its final strength, its durability, it all comes down to a chemical reaction that is incredibly difficult to get a handle on.
You know, this isn't like baking a cake where you just follow a simple recipe. It's way more like a chemical soup with all these different ingredients reacting at once. The specific cocktail of microscopic crystals and gels that ends up forming is what gives concrete its power. Getting that mix right, well, that's the whole game.
So let's dive into Section 1, Cement's Chemical Conundrum. How in the world do scientists even begin to navigate this kind of complexity? Let's break down just how big the problem is.
Okay, so to really understand what's happening in a typical batch of wet cement, you have to track at least 8 major chemical components. And they're all interacting, competing, and creating new stuff all at the same time. Trying to calculate that from the ground up? Phew! That is a truly monumental task. So that brings us to Section 2, the ternary diagram map. Faced with this crazy 8-part puzzle, scientists really needed a guide, a way to see the destination before they started the journey. And they've found one in a tool that, get this, they borrowed from geologists. And that solution is this special kind of map called a ternary phase diagram. It's an incredible technique for visualizing and predicting that final chemical mix. And like I said, it's been used for decades by geologists to figure out how different kinds of rocks form deep inside the Earth. So what is a phase diagram, really? Well, think of it as a cheat sheet for chemistry. It's a map, and it's based on the fundamental laws of thermodynamics. It basically tells you, hey, if you start with these ingredients, this is the stable stuff you're going to end up with. No guesswork. And reading one of these maps is surprisingly easy. Each of the 3 corners represents 100% of a key ingredient, so any point you plot inside that triangle is just a unique recipe blending those 3 things. You find your blend spot on the map, and boom, the region it's in tells you exactly what stable compounds are going to form. It's like a chemical GPS. Okay, on to Section 3, 2 essential cement maps. Now, for something as complicated as cement, you can't really cram everything onto a single map. So chemists rely on 2 specific maps that work together to tell the whole story. Think of these 2 maps as giving you 2 totally different but equally crucial pieces of the puzzle. The map on the left tells us about the components that give concrete its raw strength, its structural backbone. The map on the right is more about defense. It helps predict the formation of minerals that affect how it holds up over the long haul. So that first map, the one on the left, it predicts the formation of the main strength-giving stuff, the gels and crystals that make concrete super strong. The second map, on the right, helps us understand the other critical minerals that pop up, especially the ones that determine how well the concrete can resist things like chemical attacks over time. All right, Section 4, putting the maps to work. Theory is great, right? But let's see how these maps actually perform in a real-world experiment. This is where it gets really cool. So to put these maps to the test, researchers made 5 different cement blends. They started with your standard Portland cement as the control group. Then they made 4 new versions by mixing in different amounts of 2 really common additives, limestone and a reactive material called metakaolin. The big question was, could the maps actually predict what would happen in each of these unique blends? So first, they took the chemical recipe for each of the 5 blends, and they plotted it as a single point on that strength map we were just talking about. And you can see right away how adding different stuff shifts the starting point, pushing each blend into a whole new chemical territory. Then they did the exact same thing on that second durability map. And again, each point lands in a different spot, which means the map is giving them a totally different set of predictions about a whole other group of minerals that should be forming. So now, based purely on where those dots landed, the maps made some really specific calls. For example, they predicted that blend 2, the one with a lot of metakaolin, should form a very particular mineral called stratlingite. But blend 3, with all the limestone, should form something completely different, monocarbonate. And here it is, the payoff. When the researchers actually analyzed the hardened sealant samples, the results were a perfect match. These peaks you're seeing here, they're basically chemical fingerprints for different minerals. And, yep, blend 2 had stratonite and blend 3 had monocarbonate. Exactly what the maps said would happen. The theory just held up perfectly. Now, the really important thing to get here is that these diagrams aren't just a neat trick. They represent the same fundamental data that a powerful computer model would use. But while a computer spits out a bunch of numbers, the diagram gives you this intuitive visual overview. It lets you see the entire chemical landscape in one glance. Okay, let's wrap this up with Section 5, why this map matters. Because this is not just some cool lab experiment. Understanding this chemical map has huge, real-world consequences for literally everything we build. These maps are the key to helping engineers finally manage the incredibly complex dance between all those 8+ chemicals we saw earlier. It lets us move past trial and error and start intentionally designing better, more reliable materials from the ground up. With these maps, we can actually engineer concrete to face specific challenges. We can design more sustainable cements that use less energy to make, which is great for our carbon footprint. We can also predict and stop harmful chemical attacks from stuff like de-icing salts or sulfates in the soil, making our roads and bridges last for decades longer. And this whole idea of mapping out complex chemistry, it goes way beyond just concrete. It's an amazing tool for engineering all kinds of next-gen materials, from advanced ceramics to new metal alloys. So it really makes you wonder, right? If we can chart the future of something as messy as cement, what other chaotic materials are just waiting for the right map to come along and reveal all their secrets?